Welcome to the TimeForceHypothesis channel. Thank you for visiting. If the content of this channel inspires you in any way and you would like to share your thoughts, please feel free to reach out via email, timeforcehypothesis@gmail.com. I would love to hear your thoughts, good, bad, or indifferent. The first step of any new discovery is to pose a question. If you ask the question, what are the consequences of developing a comprehensive theory that can describe time, gravity, dark matter, dark energy, and other fundamental phenomena of the universe? A good answer might be, a comprehensive theory that successfully explains all these phenomena would represent a significant milestone in our understanding of the universe. The impacts of such a discovery could be profound, with potential implications across many fields. Here is a short list. 1. Physics. Obviously, the most direct impact would occur in this field, potentially leading to a new era of discovery and understanding. The holy grail within this discipline is a theory of everything. This would be a conceptual idea that unifies all fundamental forces and elements of the universe and has been the primary pursuit of physicists for decades. A theory of everything should reconcile quantum mechanics with general relativity. 2. Cosmology. Our understanding of the universe's origins, its evolution, and its ultimate fate would be dramatically improved. This could resolve many outstanding puzzles, like the nature of dark matter and dark energy, the cause of the universe's accelerated expansion, and the exact mechanism of the Big Bang. 3. Technology. New fundamental understanding of the universe often leads to technological breakthroughs. For instance, the development of quantum mechanics paved the way for the invention of many modern technologies, like semiconductors and MRI scanners. Similarly, a comprehensive understanding of time, gravity, and other phenomena could lead to unimaginable technological advancements. 4. Philosophy and metaphysics. Such a theory might also influence philosophical thought, particularly metaphysics, which is concerned with the nature of reality. Philosophers would likely engage with the implications of this new understanding, possibly leading to new or revised perspectives on time, space, causality, and the nature of existence itself. 5. Societal implications. Like any major scientific breakthrough, this could also have broader societal implications. It could influence everything from education, with new scientific concepts to be taught, to religion, with possible implications for beliefs about the universe and our place in it. Remember, the process of verifying such a theory would be rigorous and would likely take many years, as it would need to not only explain all known phenomena but also make accurate predictions about those yet to be observed. Regardless, the discovery of such a theory would be a turning point in our understanding of the universe. This is the ultimate goal of the working hypothesis that is about to be read to you. This video is a reading of the preliminary scientific paper about the time-force hypothesis that I, Mike Bermea, have developed over the past year of dedicated work. This paper describes an idea that is still very much in its infancy. I have chosen to share it prematurely as I believe the concept could be revolutionary to many different fields of study. Working alone on this project could take more than a lifetime to complete. For this reason, moving forward, I will be expressing these ideas in an open-source style format. I am open to all ideas and objections to this hypothesis as they will only serve to progress the concept further and strengthen its foundation. This first video will be audio only. However, it will be the first in a series of videos that I plan to develop that will explore this hypothesis in much more detail with the help of visual aids. I will now begin the reading of the paper I have written. I will provide a copy of the paper in the description below for those who would like to read it themselves or follow along. It is important to understand that at the time of this video this idea is still a working hypothesis and not an accepted theory in any field of study, nor has it been peer-reviewed in any way. It is simply my conceptual idea of how the universe might work. I understand that by releasing an idea in this manner I open myself up to backlash from the scientific, philosophic, and theologic communities. This is where you must understand. I just don't give a damn. Sorry, I have this idea and I am going to continue to develop it with or without acceptance or support from them. Period. That being said, please point out any and all flaws you see in my logic so I can address them. So without further ado, I present to you a reading of my hypothesis. Title: The TimeForceHypothesis, a Novel Universal Perspective. By Mike Bermea. Abstract: This paper introduces the TimeForceHypothesis, a novel cosmological model that proposes a fundamental rethinking of our understanding of the universe. Bridging gaps in current theories, the hypothesis offers a fresh perspective on the nature of time, mass, gravity, dark matter, and dark energy. It suggests that these phenomena are manifestations of a single action, the inflationary action caused by the interaction of the time force, analogous to dark energy, and a 3D fabric, related to the Higgs field, that forms a 4D hypersphere. The hypothesis further integrates these concepts with existing theories such as general relativity and quantum physics, providing new insights and interpretations. The time-force hypothesis carries profound implications for various fields, from cosmology to theology and psychedelic research, offering the potential to revolutionize our comprehension of universal phenomena. This paper provides a comprehensive overview of the hypothesis, its mathematical framework, and its potential implications, serving as an invitation to further exploration and validation of this compelling new model. Introduction. The cosmos has always been a source of profound wonder and intellectual fascination. Our pursuit to understand the universe has given birth to several intricate theories, including Einstein's theory of general relativity and the quantum field theory of the Standard Model. While these theories have been successful in explaining many aspects of our universe, there remain several unresolved questions, such as the nature of dark matter, the enigma of dark energy, and the reconciliation of quantum mechanics with gravity. Currently, the two pillars of modern physics, general relativity and quantum mechanics, operate within different realms. General relativity excellently describes the macroscopic world and gravity, while quantum mechanics provides an unparalleled description of the microscopic world. Yet, their integration into a unified theory has been elusive. Furthermore, the existence of dark matter and dark energy, essential for the current cosmological model, the lambda-CDM model, to agree with observations, are based on phenomena that are yet to be directly detected. This suggests a potential gap in our understanding of the universe's fundamental nature. The time-force hypothesis, the focus of this paper, is a novel cosmological model that suggests a new perspective to address these limitations. The inspiration for this hypothesis comes from a simple but compelling question: what if the disparate phenomena we observe in our universe are all manifestations of a single fundamental action? This overarching concept of the time-force hypothesis proposes that the inflationary action caused by the interaction between a time force, analogous to dark energy, and a 3D fabric, akin to the Higgs field, forming a 4D hypersphere, can explain these phenomena. In this paper, we explore the time-force hypothesis, its principles, and its proposed relationships between various elements of the cosmos. We explore how this new model aligns with, diverges from, and augments our current understanding offered by general relativity and quantum mechanics. We also touch on the potential philosophical and conceptual implications of this hypothesis, offering a fresh lens through which to view and understand our universe's fundamental nature. 2. The time-force hypothesis, a fresh outlook. 2.1 Time force and the 3D fabric. The cornerstone of the time-force hypothesis lies in the interaction between two fundamental components, the time force and the 3D fabric. This section aims to shed light on these two entities and discuss their interplay, resulting in the inflationary action that defines our universe. The time force, in the context of this hypothesis, is conceptually akin to what contemporary cosmology refers to as dark energy. It is a type of energy that exists within the fourth spatial dimension and is confined within the boundary of the 3D fabric. The time force is imagined as an energy source with higher intensity inside this boundary compared to the external environment. This energy differential is the primary driver for the expansion of the universe, much like the pressure difference inside and outside an inflating balloon. The 3D fabric, on the other hand, is analogous to the Higgs field in current physics. This field, a pervasive energy field that gives particles their mass, plays the role of a confining 3D membrane in the time-force hypothesis. The 3D fabric forms the skin of a 4D hypersphere, encapsulating the time force within it. Our observable universe exists as a tiny fraction within this 3D fabric. The interaction between the time force and the 3D fabric can be likened to the behavior of an inflating balloon. The time force, akin to the pressure inside a balloon, drives the inflation. It pushes against the 3D fabric, akin to the skin of the balloon, causing it to expand. The greater the time force, internal pressure, the faster the expansion, echoing the accelerating expansion of the universe we observe today. This simple, elegant analogy illuminates a key concept of the time-force hypothesis. All observable phenomena in our universe could be secondary effects stemming from this primary inflationary action occurring within the higher-dimensional space. By reinterpreting the universe's expansion through this lens, we can start to draw new connections and hypotheses about the nature of the universe and its various components. 2.2 Time, a fourth spatial dimension. In the time-force hypothesis, time takes on a unique interpretation. Rather than being an abstract, independent entity, time is viewed as our perception of movement through the fourth spatial dimension. This redefinition aligns with the idea of spacetime as a single intertwined fabric, but it also extends this concept by tying the experience of time directly to the inflationary action of the universe. To understand this perspective, consider any given point on the 3D fabric. As the universe expands due to the pressure exerted by the time force, every point on the 3D fabric is effectively moving away from a universal origin point, which can be denoted as 0, 0, 0, 0 in four-dimensional space. This outward movement through the fourth spatial dimension is what we perceive as the passage of time. It's important to note that the current velocity through this fourth dimension, or time, is exceptionally high due to the relentless acceleration of universal expansion since creation. This novel interpretation of time, as proposed by the time-force hypothesis, provides a fresh perspective on various phenomena we encounter in our daily life and in the cosmos at large. Under this model, our experience of time isn't a mere cognitive illusion, but a direct result of our existence within the inflating 3D fabric. It provides a mechanistic link between the fundamental processes driving the universe's expansion and our individual, subjective experience of time. The time-force hypothesis thus offers a unique perspective to understand and explore the intriguing and complex concept of time. 2.3 Mass, inertia in the fourth dimension. In the standard model of particle physics, the Higgs field is fundamental to the understanding of mass. Particles acquire mass through their interaction with the Higgs field, an idea confirmed by the detection of the Higgs boson. The time-force hypothesis embraces this understanding but extends it further, connecting it with the concept of inertia in the fourth dimension. Mass, under the time-force hypothesis, is viewed as the inertial property of matter being forced in one direction by the 3D fabric at an extreme velocity. This direction is that of the fourth spatial dimension, the one we perceive as time. In essence, mass is the result of the resistance to change in motion in this direction. This resistance is what we understand as inertia, which, in this context, is intrinsically tied to the fourth dimension and the universe's expansion. The inertial properties of mass thus stem from the interaction of matter with the Higgs field, which acts as the 3D fabric of the observable universe. As the universe expands, driven by the time force, objects within the universe resist this motion through the fourth dimension due to their inherent inertia. This resistance is more pronounced for objects with more mass, further solidifying the connection between mass and inertia in this framework. By redefining mass as a property emerging from the universe's expansion, the time-force hypothesis provides a direct link between the fundamental constituents of matter and the grand cosmological scale of the universe. It places the concept of mass within a dynamic, ever-expanding universal context, offering new avenues for understanding and exploring the origins and nature of mass. 3.1 Gravity and General Relativity, the topography of the 3D fabric. One of the key aspects of the time-force hypothesis is its reinterpretation of gravity. Historically, our understanding of gravity has evolved from Newton's universal law of gravitation to Einstein's general theory of relativity. Newton's law posits gravity as a force between two masses, while Einstein's theory describes gravity as the warping of spacetime by mass and energy. The time-force hypothesis offers a perspective that connects these understandings with a novel twist. The hypothesis suggests that gravity, as Newton described, is an emergent force caused by the acceleration of universal expansion. The fabric of the universe, the 3D fabric, is continually expanding due to the time force's influence. When mass is introduced into this framework, it resists this expansion due to its inherent inertia, causing the 3D fabric to deform around it. This deformation is what we observe as gravitational attraction. General relativity's role in this picture is to provide a topographic map of these deformations. The equations of general relativity describe the curvature of spacetime around massive objects, which, in the time-force hypothesis, translate into the deformation of the 3D fabric. In other words, Einstein's equations serve as a key to understanding the topography of the 3D fabric and its alterations due to mass. This perspective obviates the need for spacetime as a separate entity. Instead, spacetime can be viewed as a proportionality constant that describes the 3D fabric's topography with respect to the time dimension. The curvature of spacetime described in general relativity then becomes equivalent to the deformation of the 3D fabric due to the presence of mass, and Einstein's description of gravity emerges as the result of this warping. By reinterpreting gravity in this way, the time-force hypothesis bridges the gap between the macroscopic and microscopic scales, unifying the forces of nature and providing a coherent framework that connects the expansion of the universe with the behavior of the smallest particles. In essence, the Higgs field becomes the 3D stage of our observable universe, and general relativity describes the shape of that stage within the fourth dimension of time. 3.2 Dark matter and dark energy, a unified perspective. The time-force hypothesis provides a fresh reinterpretation of two elusive concepts, dark matter and dark energy. Conventionally, theories postulate the existence of dark matter to account for certain observed gravitational anomalies. Similarly, dark energy has been invoked to explain the observed accelerated expansion of the universe. These perplexing aspects find novel and intriguing explanations within the time-force hypothesis. This unique framework introduces time as a fourth spatial dimension, proposing a mechanistic explanation for these phenomena through the interplay between the higher dimensional energy and the three-dimensional, 3D, fabric, Higgs field. The time-force hypothesis attributes the effects of dark matter not to undetectable particles but to the residual warping of the 3D fabric resulting from persistent exposure to mass. Areas with a significant presence and movement of matter are thought to develop increased deformation in the 3D fabric, akin to deepening ruts on a well-trodden path. This persistent deformation would account for the gravitational effects currently attributed to dark matter, such as the rotation curves of galaxies. In regions of high matter traffic, such as around galaxies and large-scale structures, the 3D fabric would exhibit greater deformation, hence producing the illusion of additional, unseen mass. Simultaneously, the time-force hypothesis provides an alternative explanation for the accelerated expansion of the universe by replacing the concept of dark energy with the time force. The time force is the energy confined within the 4D hypersphere, resulting in an inflationary action akin to the positive pressure within an inflating balloon. The hypothesis postulates that the Big Bang event generated a surplus of energy trapped within the 4D hypersphere. This residual energy, being greater than the energy in the fourth-dimensional space outside the hypersphere, is the driving force behind the universe's expansion. The time force, therefore, serves as a more tangible and mechanistic explanation for the expansion, rooted in the interaction between the higher dimensional energy and the 3D fabric. Further, it is proposed that the time force exerts an outward push, while the inertial properties of matter resist this outward thrust. This resistance slows the rate of local acceleration on the surface of the 3D fabric, leading to an exaggerated topography observed as dark matter phenomena. In essence, regions of space abundant with mass experience the inertial resistance of matter more frequently, causing a greater deformation of the fabric than areas of the cosmos that are relatively empty. By providing a unified perspective on dark matter and dark energy, the time-force hypothesis offers a coherent and intuitive explanation for the observed cosmic behaviors. This understanding connects directly to the fundamental interactions between higher-dimensional energy and the 3D fabric. This suggests that small modifications to the equations of general relativity to incorporate a mass exposure time factor could account for these residual deformations, allowing the framework of general relativity to calculate dark matter. 4. Mathematical framework, deriving a plausible 4D hypersphere. In this section, we will demonstrate how working backward from the Hubble constant, as the rate of the 3D fabric stretching, can help us derive a plausible 4D hypersphere that could house our universe in a manner consistent with our observations. The Hubble constant, denoted as h0, represents the current rate of expansion of the universe. By assuming that this value represents the rate at which the 3D fabric is stretching, we can gain insights into the properties of the proposed 4D hypersphere. First, we recall the Hubble constant's value as approximately 70 kilometers per second per mpc. Using this constant, we can calculate the Hubble time, which is the reciprocal of the Hubble constant and provides an estimate of the age of the universe. T_H1/H0 13.8 billion years. Now, let's consider the Hubble sphere, a sphere centered on an observer beyond which objects are receding from the observer faster than the speed of light due to the expansion of the universe. Its radius is calculated as R_HS equals C/H0 14.4 billion light-years. The Hubble sphere serves as a useful starting point for understanding the size of the observable universe. However, to derive a 4D hypersphere that could house our universe, we must look beyond the Hubble sphere and analyze the universe's expansion in 4 dimensions. Using the square-cube law, we can relate the stretching of the 3D fabric to the expansion of the 4D hypersphere. The square-cube law states that as an object grows in size, its volume increases more rapidly than its surface area. In our case, the volume of the 4D hypersphere is proportional to the cube of its radius, while the surface area, where the 3D fabric resides, is proportional to the square of its radius. By equating the rate of change of the surface area, our Hubble constant, to the rate of change of the volume, we can derive the radius of the 4D hypersphere. Once we have derived the radius of the 4D hypersphere, we can calculate its surface area and curvature. The surface area of a 4D hypersphere is given by the equation A equals 2π2r⁻3. With the calculated surface area of the 4D hypersphere, we can determine how many observable universes can fit on its surface, providing a better understanding of the scale of the 4D object. Furthermore, by analyzing the curvature of the 4D hypersphere, we can assess its compatibility with current observations of the universe. In conclusion, by working backward from the Hubble constant as the rate of 3D fabric stretching, we can derive a 4D hypersphere that could plausibly house our observable universe. This approach allows us to connect the expansion of the universe with a higher dimensional object and explore the implications of the time-force hypothesis. This section presents a mathematical exercise to derive a hypothetical 4D hypersphere that could be consistent with observational data, including the derivation of key equations and relationships between various constants, variables, and the implications of the hypothesis for the size, shape, and curvature of the universe. This exercise is for plausibility's sake only, and the values derived are not being claimed as actual values for our universe. More in-depth calculations would be necessary to determine accurate numbers and are outside of the scope of this paper. These calculations will obviously be conducted as this hypothesis matures into theory. To develop a mathematical framework for the time-force hypothesis, we will work backward from the Hubble constant as the rate at which the 3D fabric is stretching. The Hubble constant, h0, is approximately 70 kilometers per second per mpc, which we will use as the basis for our calculations. We first convert the Hubble constant to a more convenient unit. h0 70 kilometers per second per mpc *, 1 mpc/3.09 by 1019 kilometers. h0 2.27 times 10 to the power of -18 s1. Using the Hubble constant, we can determine the radius, r, of the 4D hypersphere by applying the square cube law. R equals c/h0. R 3 times 10 to the power of 8 m divided by s divided by 2.27 times 10 to the power of negative 18 s1. R 1.32 by 1026 m. Next, we calculate the surface area, A, of the 4D hypersphere using the formula. A equals 2 * pi 2 * R3 A2 * pi 2 * 1.32 by 1026 m, 3. A 3.79 times 10 to the power of 78 m2. To determine how many observable universes can fit on the surface, we need the surface area of our observable universe. The radius of the observable universe is roughly 4.4 by 1026 m. Using the surface area formula for a two-sphere, A underscore OBS equals 4 * pi * R underscore OBS 2. A underscore OBS 4 * pi * 4.4 by 1026 m, 2. A underscore OBS 2.44 times 10 to the power of 54 m2. Now, we divide the surface area of the 4D hypersphere by the surface area of the observable universe. Number of observable universes A/A underscore OBS. Number of observable universes 3.79 times 10 to the power of 78 m2 / 2.44 times 10 to the power of 54 m2. Number of observable universes 1.55 by 1024. Lastly, we calculate the curvature of the surface of the 4D hypersphere. The sectional curvature K is given by K equals 1/2. K1/ 1.32 by 1026 m, 2. K 5.75 times 10 to the power of negative 53 m2. In summary, the time-force hypothesis, with the Hubble constant as the rate at which the 3D fabric is stretching, leads to a 4D hypersphere with a radius of 1.32 by 1026 m, a surface area of 3.79 times 10 to the power of 78 m2, and a sectional curvature of 5.75 times 10 to the power of negative 53 m2. The mathematical framework produced in this section results in an extremely small positive curvature value, K 5.75 times 10 to the power of negative 53 m2. This calculation is not entirely inconsistent with current observations of the universe's near flatness. Furthermore, calculated that approximately 1.55 by 1024 observable universes can fit on the surface of this hypersphere. This suggests that the observed universe might be but a tiny fraction of the whole universe. As aforementioned, these calculations are for demonstrational purposes to illustrate plausibility. What we can conclude with this exercise is that we cannot outright dismiss the time force's proposal with simple back-of-the-napkin calculations. 4.1 Mathematical Integration and Consistency with General Relativity. In this section, we will explore the consistency of the time-force hypothesis with general relativity and examine its compatibility with Einstein's field equations. General relativity describes the fundamental interactions between mass energy and the geometry of spacetime presented in a new light by this hypothesis as the topography of our 3D fabric. Einstein's field equations are at the core of this theory and can be written as G caret mu equals 8 pi G / C caret 4 T caret mu, where G caret mu is the Einstein tensor, which describes the curvature of spacetime, G is the gravitational constant, C is the speed of light, and T caret mu is the stress energy tensor, representing the distribution of mass energy in spacetime. To demonstrate the consistency of the time-force hypothesis with general relativity, let's derive a modified stress-energy tensor for the time-force hypothesis. The stress-energy tensor T caret mu represents the distribution of mass energy in spacetime and is composed of different forms of energy densities, pressures, and energy fluxes. For the time-force hypothesis, we must account for the additional energy densities and pressures associated with the 4D hypersphere and the time force. Let's first consider the standard stress-energy tensor in a homogeneous and isotropic universe, which can be written as T caret mu equals rho plus P, U caret nu P G caret mu. Here, Rho is the energy density, P is the pressure, U is the velocity of the matter, and G nu is the metric tensor. Now, let's add the additional energy densities and pressures arising from the time force hypothesis. We will introduce the following terms. 1. Lambda G nu, the contribution from the cosmological constant lambda. 2. F nu, the energy momentum tensor associated with the time force. The modified stress energy tensor for the time force hypothesis can now be written as T nu equals rho plus P, U nu PG nu plus lambda G nu plus F nu. In this modified stress energy tensor, F nu represents the energy momentum tensor associated with the time force, which includes the additional energy densities and pressures resulting from the stretching of the 3D fabric within the 4D hypersphere. The specific form of F nu will depend on the properties and behavior of the time force, and further theoretical developments are necessary to precisely define it. However, the inclusion of the F nu term in the modified stress energy tensor demonstrates how the time force hypothesis can be integrated into the framework of general relativity by accounting for the additional energy densities and pressures associated with the hypothesis. When we incorporate the time force hypothesis into the framework of general relativity, we must account for the additional terms in the modified stress energy tensor. We can do this by modifying the standard Friedmann equations that describe the expansion of the universe to account for the effective energy density ρ_EFF and the effective pressure P_EFF derived from the modified stress energy tensor. H squared equals 8 pi g/3 ρ_EFF k/a2a/a equals dash 4 pi g/3 ρ_EFF plus 3p_EFF. By introducing these modified Friedmann equations, we incorporate the time force hypothesis into the framework of general relativity, demonstrating that the time force hypothesis may be mathematically consistent with the Einstein field equations. Furthermore, the equations of motion and the evolution of the 3D fabric can be described using this modified stress energy tensor in conjunction with the adapted Friedmann equations. The modified stress energy tensor, along with the derived Friedmann equations, demonstrates that the time force hypothesis is compatible with Einstein's field equations, supporting the plausibility of the hypothesis in the context of our current understanding of the universe. 5.1 Cosmological implications, describing motions of large-scale structures with the time force hypothesis. The time force hypothesis could have significant implications for our understanding of the movements of large-scale structures, such as galaxies and galaxy clusters. Specifically, the concept of a 4D hypersphere and the stretching of the 3D fabric within it may provide a new perspective on the observed motions and the large-scale structure of the universe. Galaxy clusters and superclusters. Under the time force hypothesis, the 3D fabric of our universe is expanding within a 4D hypersphere. This expansion is assumed to be homogeneous and isotropic, meaning it's the same in all locations and directions. This premise might provide an explanation for the large-scale distribution of galaxies, which we observe to form a cosmic web of clusters and superclusters. The homogeneous and isotropic stretching of the 3D fabric could naturally lead to such a structure, with galaxies forming in regions where the stretching has been inhibited by the matter, resulting in a valley or low-lying region. Matter might flow throughout our cosmos like water flows on Earth, seeking the lowest areas. Matter seems to seek the path of least resistance through time, and these low-lying areas would require less energy for time progression due to that region's reduced velocity through time when compared to the surroundings. Galaxy rotation curves. The observed rotation curves of galaxies, which show the speed of stars as a function of their distance from the galactic center, are a long-standing puzzle in astrophysics. The time force hypothesis, through the proposed modifications to the stress energy tensor, could potentially contribute to a more accurate description of these rotation curves. The additional terms in the modified stress energy tensor might account for the missing mass that is currently attributed to dark matter. Cosmological redshift, the redshift of distant galaxies, which provides evidence for the expansion of the universe, could also be reinterpreted under the time force hypothesis. The stretching of the 3D fabric might be directly responsible for the redshift, as the stretching could increase the wavelength of the light traveling through space, leading to a shift towards the red end of the spectrum. Cosmic Microwave Background, CMB. The CMB is a snapshot of the universe around 380,000 years after the Big Bang, showing tiny temperature fluctuations that correspond to density fluctuations in the early universe. The time-force hypothesis might offer a new interpretation of these fluctuations. The initial conditions of the 4D hypersphere and the resulting rate of 3D fabric stretching could have influenced the size and distribution of these density fluctuations. Moving forward, it will be essential to develop the mathematical formalism of the time-force hypothesis further, enabling precise predictions about these and other cosmological phenomena. Computational simulations based on the time-force hypothesis could be particularly valuable, allowing us to visualize the implications of the hypothesis for the large-scale structure of the universe. Furthermore, observational tests should be designed to verify or falsify the time-force hypothesis, ensuring its consistency with empirical data. Ultimately, the time-force hypothesis plausibly presents potential new directions for our understanding of the cosmos and its grandest structures. 5.2 Quantum Physics, easing the explanation of gravity to focus on other phenomena. One of the most profound implications of the time-force hypothesis lies in the realm of quantum physics. Since the dawn of quantum mechanics, physicists have been trying to reconcile the principles of quantum physics with general relativity, particularly in understanding the nature of gravity. The time-force hypothesis could provide a significant relief in this regard. In conventional physics, gravity is a force that interacts at both macroscopic and microscopic scales. This creates a significant challenge in integrating it into the framework of quantum mechanics, which primarily describes the microcosm. The problem arises when we try to quantize gravity, i.e., describe it in terms of discrete, quantized units akin to how we describe other fundamental forces in nature. Attempts to do so have so far resulted in non-renormalizable theories, indicating that our current understanding is incomplete. The time-force hypothesis presents an intriguing way out of this conundrum. By attributing the expansion of the universe to the stretching of the 3D fabric skin of a 4D hypersphere, we remove the necessity for gravity to explain this cosmological phenomenon. This adjustment might allow physicists to focus their attention on other aspects of quantum physics. Instead of trying to force gravity into the quantum realm, we could focus on understanding better the Higgs field or the three other fundamental forces, electromagnetism, the strong nuclear force, and the weak nuclear force, and the quantum phenomena they govern. Furthermore, this could also pave the way for new explorations into quantum phenomena, like quantum entanglement and quantum computing, without the added complexity of gravity. However, it should be noted that these implications are speculative at this stage. More in-depth exploration and research into the time-force hypothesis are needed to understand its full ramifications on quantum physics and our understanding of the fundamental forces. With quantum physics potentially relieved from the burden of explaining gravity, it opens up intriguing possibilities and fresh perspectives not just in the realm of science, but also in our understanding of life, existence, and even theology. In the next section, we investigate the theological implications of the time-force hypothesis and discuss how this concept might reconcile scientific and religious perspectives. 5.3 Theological Implications, Reconciling Scientific and Religious Perspectives. The time-force hypothesis, while a scientific proposition, could also have profound implications for theology and our understanding of spirituality. Science and theology have often been seen as distinct, sometimes even conflicting, domains. However, the time-force hypothesis might offer a pathway to reconcile these perspectives. One of the central tenets of many religious and spiritual beliefs is the concept of transcendence, the idea that there are realities beyond our observable universe. The notion of a 4D hypersphere housing our 3D universe aligns with this belief, providing a scientific model that could be used to explain spiritual experiences and concepts. Furthermore, the time-force hypothesis could also help address the question of creation. The idea of a universe expanding within a higher dimensional space could provide a new perspective on the origin and the evolution of the universe, possibly aligning with various religious narratives about the beginning of existence. Moreover, the time force hypothesis might help address the apparent dichotomy between determinism and free will. If time is a force that shapes the universe's fabric, it could suggest that while the cosmos follows deterministic laws, the unfolding of events within that cosmos, including human actions, might still allow for a degree of freedom. This could provide a satisfying resolution to the tension between scientific determinism and the religious concept of free will. It's essential to emphasize that these implications are speculative and should not be considered as endorsing or contradicting any specific religious beliefs. The aim here is to show how a scientific hypothesis could potentially interact with and illuminate theological and philosophical questions. As we continue to explore the implications of the time force hypothesis, it's not only the vastness of the cosmos or the abstract concepts of theology that come into play. Surprisingly, this hypothesis might also shed light on the intricacies of human consciousness, particularly as experienced during altered states induced by psychedelic substances. In the next section, we will probe into the potential connections between the time force hypothesis and the study of psychedelic experiences. 5.4 Psychedelic Research, Time Force Hypothesis, and the Understanding of Psychedelic Experiences. With the reemergence of psychedelic research gaining momentum in modern society, the time force hypothesis could potentially shed light on the perplexing experiences induced by psychedelic substances. Since the majority of these substances influence consciousness by attenuating the focus on our 5 physical senses, the time force hypothesis might provide a framework to understand what occurs during these altered states. Psychedelics often induce experiences characterized by time distortions, such as time dilation or compression, and complex, hyperdimensional visuals. These experiences may be reflective of our consciousness gaining a heightened sensitivity to the 4th dimension, the time dimension. Under the influence of psychedelics, our consciousness might be free to experience this time realm unencumbered by the overwhelming input of our physical senses. This perspective aligns with the time force hypothesis, which posits time as the 4th spatial dimension in which our 3D fabric as the skin of an expanding 4D hypersphere is suspended. Could it be that we have the capacity to perceive this 4th spatial dimension through extreme suppression of our physical senses? The time force hypothesis could also provide insights into the striking parallels between psychedelic experiences and other altered states of consciousness, such as near-death experiences, deep meditative states, and dreamlike states. All these experiences share common elements, such as a sense of transcending physical reality, experiencing non-ordinary dimensions, and the profound alteration of temporal perception. According to the time force hypothesis, these similarities might arise from our consciousness's capacity to perceive the time realm when the dominance of physical senses subsides. Psychedelic-induced visuals often exhibit a multidimensional nature that seems to defy the constraints of 3-dimensional space. This could be interpreted as a subjective encounter with the higher dimensional space within which our universe resides, as postulated by the time force hypothesis. It is important to approach these speculative connections between the time force hypothesis and psychedelic research with a rigorous scientific mindset. While the intersections between these areas of inquiry are undeniably fascinating, establishing any definitive links between them will require comprehensive research and empirical evidence. In sum, the time force hypothesis offers intriguing possibilities for understanding the nature of psychedelic experiences, alongside its broader implications for cosmology, quantum physics, and theology. Exploring this radical new idea, we may unlock new perspectives on the nature of our universe and the profound complexity of human consciousness. Conclusion: the potential of the time force hypothesis. Throughout this paper, we have explored the proposal of the time force hypothesis, a novel perspective that introduces time as a 4th spatial dimension within the framework of a 4-dimensional hypersphere. This hypothesis, although speculative and in need of rigorous testing, presents a revolutionary approach to understanding various aspects of our universe, spanning from cosmology and quantum physics to theology and the burgeoning field of psychedelic research. In the realm of cosmology, the time-force hypothesis provides a new way to understand the motion of large-scale cosmic structures like galaxies and galaxy clusters. Rather than solely attributing their movements to gravity, this hypothesis suggests that the inherent curvature of our 3D fabric within the 4D hypersphere suspended in the time dimension plays a significant role in these celestial dynamics. The time-force hypothesis also has the potential to offer new insights in the field of quantum physics. By conceptualizing time as a fourth spatial dimension, the hypothesis could alleviate the quantum world from the task of explaining gravity, a long-standing challenge in the pursuit of a unified theory. This shift could allow researchers to concentrate more intently on other quantum phenomena. In the sphere of theology, the time-force hypothesis may provide a platform that could help reconcile scientific and religious perspectives. By proposing that our universe is embedded within a higher dimensional space, it opens the door to discussions of transcendent entities and realities, fostering a dialogue that values both scientific and spiritual viewpoints. Perhaps one of the most intriguing aspects of the time-force hypothesis is its potential connection to psychedelic research. This hypothesis could offer a framework to understand the reported alterations in the perception of time and space during psychedelic experiences. It might suggest that these experiences, as well as near-death episodes, deep meditative states, and dreamlike states, are manifestations of increased sensitivity to the fourth dimension, time, when the dominant input of our physical senses is diminished. In summary, while the time-force hypothesis awaits further validation and empirical support, it brings forth a bold and innovative perspective on our universe. It encourages us to reconsider time, not as a passive backdrop where events take place, but as a dimensional aspect intertwined with the very fabric of our reality. As we continue to explore and scrutinize this hypothesis, we may discover that it has the potential to significantly transform our understanding of the universe and our place within it. By opening new avenues for research and dialogue across diverse fields of study, it challenges us to expand our conceptual horizons and redefine our perception of reality. This has been a reading of The Working Hypothesis conceptualized by Mike Bermea. If you made it this far, please like, share, and subscribe. Remember, this is only what I think. Please let me know what you think in the comments below.